circles unit. So we're going to first talk about some definitions. So first of all, central angles in circles is what we're going to talk about first, and then we'll be doing lengths of arcs. So a central angle is formed by starting from the center of the circle and working its way out. Does everybody see how we have this line and this line making up this angle theta? Yeah. Now it's called a central angle if it starts from the center of the circle and works its way out. So see how it starts in the center and works its way out. For it to be a true central angle, it has to start right in the center of the circle. Okay, so next thing, a minor arc. So a minor arc is the intercepted arc from the central angle. So does everybody see how this central angle opens up on that green arc? Yeah. Do you see how it opens up onto the green arc? Well, that would be called the minor arc. So that's arc AB, minor arc AB. Does everybody see how minor arc is opened up from the central angle? Now a major arc is the major arc, the arc that's bigger, and it eats the minor arc. So I like to say it eats because it surrounds the minor arc. So the major arc surrounds the minor arc. It's the blue arc in this problem. Does everybody see that? Now a couple things to note. A minor arc will always be written with 2 points, simply AB. A major arc, so that you can specify a major arc, you have to write 3 points on the major arc. So instead of saying arc AB, I could go around and say AB for a major arc, but that would be the same as AB minor arc. So that's why for the major arc we would have to say ACB. Does everybody see how to write a major arc versus minor arc? So the reason we have to do 3 points on a major arc is so that you can make sure you follow around in the right direction. Now a couple things just to note. If I was to put another point on here such as E, a major arc can be written by any 3 points. I mean, A and B would have to be the same, but the same major arc, AEB, is the same thing as ACB. Does everybody see what I'm saying?
You don't have to write the 4 points even if there are 4
Yeah,
points.
good question. No, you don't have to write the 4 points even if there are 4 points. It only takes 3, and you can use whichever ones. Does that make sense, everybody? Okay, sweet. So every minor arc will have a major arc that eats it. Once again, a central angle starts from the center of the circle and works its way out. So let's go through, let's name the major arcs and the minor arcs. So take my suggestion, I always write the minor arc and then I go to the major arc and write the major arc that surrounds it. So the first minor arc I'm looking at is AB or BA, it doesn't matter. So minor arc AB. Once again, that's the minor arc because do you see how we have a central angle that works its way out? Are we good?
Yes.
Okay, so let's now name the major arc that intercepts that minor arc. So the major arc. So it would be, for example, B, we wouldn't go BA, we're eating it. So B, then C, then A. Does that work? No, D wouldn't work. That wouldn't eat the minor arc.
B, then D, then A. Yeah.
B, then D, then A works as well. Does everybody see how that's the major arc surrounding the minor arc?
B.
So the major arc that surrounds minor arc AB would be B, D, A. That works. Questions on that? Does everybody see? Now look, a couple things to notice. Do you see how AB, AB, they land on the ends? Do you see AB, AB? Is everybody good with that? Which makes sense, right? I mean, it's going to land on the same endpoints. Okay, let's do the next minor arc here is BC. So minor arc BC. So the major arc would be CD. A wouldn't eat it. Nope. No, it wouldn't. C, then D, then A. That leaves off that whole section.
EDC.
So C, D, B works. Questions on that? Am I not being clear?
No.
Okay. So then another minor arc would be CD. Once again, your endpoint should end with CD. So
BAC.
you can't start with B. That's not where it starts.
DAC.
Guys, I can't tell if you're being serious or not. Because if you're not understanding. Let's start. Starting with C, then A, then D. Would that work? Yeah?
Yes.
Okay, C-A-D.
CDA.
CDA wouldn't work.
Yeah, right.
Okay.
Right.
Okay, and then another one. This is a
D.
minor arc, right? It is a semicircle as well, but it's still considered a minor arc because that's still a central angle, right? Opening up on an arc. So our minor arc there is AD or DA, it doesn't matter. So the major arc that opens up on it would have to be this way, right? And we'd have to do 3 points. So D, C, A. That would work. Is everybody comfortable with that? Questions?
If it was DBA, would that still be right?
That would be exactly right as well. DBA still ends in the right spot, right? You just chose the other point, which is fine. Okay, let's make some semicircles here. Semicircle means halfway around a circle. So wouldn't this be a semicircle?
Yep.
Yes.
And then wouldn't this be a semicircle?
Yes.
Are there any other combinations of semicircles?
Yeah.
Not in this one, right? Okay, so we have 2 semicircles. Now semicircles can be named with 2 points or 3. It doesn't matter. So this semicircle would be AB, right?
Okay.
And then another semicircle would be, if you said DA, didn't we already list that one?
Yeah.
Okay, so we would need to go DCA to list the other one. Does that make sense? Or DBA works. What?
Do you have to do another semicircle using the other point or no?
Only on the second one.
Well, there's not any other semicircles. We just have the green semicircle and the yellow, so we've just named both of those.
Right, but we don't have to put another semicircle because there's another point in it.
On the yellow one. We just choose one.
Like, oh, you're asking, like, with the semicircle, could we have named it DCDA?
No, but no.
Okay. Because there's no other semicircles here.
Right, but you don't so since we already did DBA, do we have to do DCA or why don't?
No, because that'd be the same thing, right? Remember, the middle point doesn't matter, right? It ended in the same spot. Does that make sense?
Yeah.
Okay. Sweet. So, do problem number 1. Ready to go. Just want to be clear on something. So, if this is a minor arc, guys, then the major arc would have to start at that same spot and end at the same spot, but you're going around the big side. Does everybody understand that? So the end points, like if this was A and B, your minor arc will be arc AB, and then let's say this is point C, so your major arc will have to end at AB. Doesn't it still end at AB?
Yeah.
It's just going around the big way. So like,
DCA.
or ACB, right? Either way. So your minor arc that relates to your major arc should have the same endpoints, because the one starts where the other one stops. Okay. Okay, so next thing. I want you to recall, if we have a triangle, if we have a circle, and we have it split up into angles, wouldn't all the angles of the circle add up to be 360 degrees?
Yeah.
Yes, okay. Now these are all central angles because we start from the center of the circle and work our way out. Now looking here, these are all central angles as well. We start from the center of the circle and work their way out. Well, if we're dealing with a semicircle, won't those 2 angles, those straight line angles, add up to be 180? So wouldn't this add up to be 180? Okay, good. Okay, so with that in mind, here's our first theorem. So if you have a central angle, you'll want to write this down. If you have a central angle, then it will be equal to its intercepted arc. Now, intercepted just means the arc it opens up on. So if you have a central angle theta, theta will be equal to its intercepted arc. So theta will be equal to the measure of AB. So theta is equal to the measure of arc AB. So once again, you have to make sure though that you have a central angle. It starts at the center of the circle and works its way out. If that's true, then theta will equal arc AB. Is everybody good with that?
Is there such thing as a non-central angle?
Yes. Let me show you an example. We'll get to them in this unit. Did that start from the center of the circle and work its way out? No. So this would not be a central angle. So this wouldn't be true. This angle would not equal its
Is
arc.
there a different?
Yeah, there is. We'll learn that later. Okay, so a central angle is equal to its intercepted arc. So look at this one. Is this a central angle?
No. Yeah.
Did it start from the center of the circle and work its way out?
Yes.
Yes, so it's a central angle. Therefore, this angle is equal to this arc. So what's the arc? 65 degrees. So the measure of this arc is 65 degrees. Pretty simple, right, guys?
Yeah.
Okay, so a couple more.
Wait, that's under group. You're doing another one. Sorry.
No, you're good. You're good. Okay, so I'm asking you to find the measure of the highlighted arc. So first of all, are we dealing with central angles?
Yeah.
Yeah, okay. So now look, it's this angle and this angle, okay? Now, we have no idea what this angle is, but we do actually. What is it?
210.
180 degrees. Okay, so then let's think about it. If this is 30 degrees, it's a central angle. Won't this arc from here to here be 30 degrees?
Yes.
If this is 180 degrees from here to here, it's a central angle and it's opening up on that arc. Won't this be 180 degrees? Is everybody good at that? So the total arc length of that would be, what would it be?
230.
210 degrees. Does everybody understand why?
Yes.
180 plus 30. Okay, let's do this one. So now we're finding the measure of the highlighted thing. So now we're finding theta. Well, first of all, we're given the arc is 110 degrees. Is theta a central angle?
Yes.
So isn't the angle equal to its arc?
Yes.
So what's theta?
110 degrees.
110 degrees. Questions on that? Okay, looking at this one, we're finding the measure of the arc. Aren't these central angles? Yes. Right? So the arc is from here to here. So won't we be adding up those angles? So that would be, and if these are 90 degrees, then an central angle is equal to its arc. So that would be 90 degrees. Is everybody comfortable with that? Okay, so let's just quickly go through this one, then I'll let you work for a while. Here we go. So looking at this picture, we're going to answer these questions. What's arc DE, BC, so on. So don't we need to go through and kind of fill in everything we can on this circle? Okay, so let's start here. If this is 30 degrees, it's a central angle. What's arc AB? 30 degrees. Okay. Now don't we have a semicircle from here to here? So won't this angle be 180 minus 30? So this is 150 degrees. Is everybody comfortable with y?
Yes.
Well, if that's 150 degrees, what's the arc? 150 degrees, because that's a central angle. Are you comfortable so far? Okay, let's look. Don't we have another semicircle from here to here?
Yes.
Yes. Okay. So then, if that's true, what angle is this?
30.
30. Does everybody see why? So this is 30 degrees. Now look, it says slash slash. Doesn't that mean those angles are equal? So if this is 30 degrees, what's this? 30 degrees. Now if those central angles are 30, the arcs are 30. So this arc is 30. And then all we're left with right here is, well, let's see. We can do this two different ways. We can do 360 minus all that stuff. Or we can say we know that from here to here is 180 degrees, correct? So 180 minus 60. So if that's 120, that's 120. So now that we've filled in our circle, we can answer all these questions. Let's answer it. What's our D to E? Follow it in that order. From D to E. 30 degrees. What's our B to C? B to C. 120 degrees. What's our BCA? You have to go in that order. Did you all listen to what I just said?
BCA.
B, then to C, then to A. So I start with B. Now I'm going to highlight this one. Starting with B,
330.
then to C, right? Then to A. Now I'm stopping at, do you see how I stopped at B and A? Started at B, went to A. Is everybody good? So now let me just add those up. So you could do it two different ways. You could add up all that highlighted part, or you could do 360 minus 30. It will come out the same, won't it? So it's 330 degrees. Questions on how I did that part? Yes.
You said you have to start at B. Why do you have to start at B?
Well, if you started with A, then went to C, then to B, that would be okay. What I'm saying is people will sometimes skip around and go from B, then A to C, and it will get all jumbled. Does that make sense? So good question. You could actually do A, C, B, same thing. As long as you keep that C in the middle.
A, C, D, C. C to B to A.
Okay.
That still works somewhere.
No, C to B to A would be that,
Oh.
in that order, right?
I was thinking.
Okay, so D, so let's go. D, E, A. So I start at D. I'm going to do it in a different color. So D, then to E. So that'd be this way, then to A. Wouldn't that be that arc? So add that up, what do we get? 180 degrees. Okay, good. And then it says find angle BFC. So this is angle. So B, then F, this is F. Sorry, the middle thing's F. I didn't write that in there. BF. Oh, no, I did write it in there. It's just covered by my 150. BFC. So what angle was that? 120 degrees. BFC. Okay. Go. Do those two problems. Okay. All right, so first of all, we just learned a central angle is equal to its intersected arc. So, for example, if this angle is 45 degrees, the measure of this arc is 45 degrees, correct?
Right.
Now, fun fact for you. You can take any degrees and rewrite it as a radian instead of degrees. So if this is 45 degrees, we know this is 45 degrees, like you said. But 45 degrees can be written as a radian, which is pi over 4. So Now, right now, you don't know how to write it as a radian. I'll teach you that. But I just want you to understand that, first of all, right now, 45 degrees is equal to pi over 4. This is written in degrees. This is in radians, okay? Now, the reason we like radians sometimes, especially for physical length, or defining arc length, is because pi over 4, can't we just calculate that as a number? Take your calculator. Isn't pi just a number? Approximately 3.14. I want you all to take your calculator. Type in pi divided by 4. That's 0.78, right?
On the ACT, said what's a radian? What is it?
I'm going to keep explaining. I wasn't quite finished. So, pi over 4 is equal to 45 degrees. But this is in radians, this is in degrees. So once again, the reason we like radians is because you see how 0.78 is a physical length. So now you know that's not only 45 degrees, but that's 0.78 of the full circle. So with that being said, let's think about why we would maybe want to use radians over degrees. If you're an engineer and you're building like let's say that you're in charge of getting the sewer ponds for a new town, and they want you to build a certain sewer pond, and they say build a sewer pond. I only don't need a section of the sewer pond. We don't need the full circle of the sewer pond, so just do it 45 degrees of a circle. You're going to be like, well, how do I know exactly how far that is? But instead of giving them the 45-degree answer, they would say, do 0.78 of a full circle. Does that make sense? Or 0.78 of the 2 pi, yes.
Does that equal 1, just 1, equal full circle?
Great question. No, a full circle is 2 pi. A full circle is 2 pi, because 360 degrees is 2 pi, but we're not there yet. Let's stay with me. I promise I've thought all this through. Okay, so this is how you take something and take it from degrees to radians. They're equal. One's a measure, one's a physical length. Does everybody understand? Degree is a measure and radians is a physical length. This is how you can take anything written in degrees and change it to its physical length form. Its radian form. You take the degrees, theta, and you multiply by pi over 180 degrees. So you take theta and you multiply by pi over 180 degrees. That will put it in its equal form, but it will take it from degrees to radians. Once again, the reason we like radians is because that gives us a physical length, not a degree length. Now they are equal, but just different ways of writing them. So, for example, if I wanted to ask you, what is 45 degrees in radians? Instead of wanting the degrees, I want the physical length of that. You're going to take the degrees and change it to radians. So you take theta, which is 45, and you multiply by pi over 180. So we're going to be multiplying by this. So you take 45 degrees, you multiply it by pi over 180. Now let's think about it. If we're multiplying fractions, don't we multiply straight across? So won't that be 45 times pi on top?
Why don't you do 360?
Because that's just a fancy 1. Otherwise, we'd be changing it. That's just a fancy 1. Because pi is 180. This is in radians. This is in degrees.
Okay.
Okay, so 45 times pi on top, and then 1 times 180 is 180 on bottom. Does everybody see how to do that? Now, you'll take your calculator. Now, listen. You will not type in pi. Otherwise, your calculator cannot put it back in a fraction. If you type in pi in your calculator, that is an irrational number. Your calculator will not be able to put it back in a fraction. So did you all hear me? Do not type in the pi part in your calculator. We want to simplify this fraction, not with pi. We're going to leave pi alone for a minute. So take 45 divided by 180. Everybody should be doing it. You get 0.25, correct? We would rather have the fraction answer, so change it back to a fraction. 1/4. So this simplified to be 1 over 4. So 45 degrees is pi over 4. Because isn't 1 times pi? And over 4. Is everybody good with that? So once again, guys, 45 degrees is actually equal to pi fourths. This is the measure. This is the physical length. Is everybody good with that? Yes.
Take a circle and just cut it apart and see the part from.
Yes, but not all, so this one was a pretty, one where you can cut it up pretty easily, but not all degrees are going to come out nice and pretty. This is way easier than doing that, but yes. Okay, so let's go ahead and, so looking at these pictures here, if this central angle is 60 degrees, then this arc is 60 degrees. But once again, I'm asking you, what's the physical length? So don't we need to change 60 degrees to radians? So we know we take 60 degrees and multiply by pi over 180, right? So wouldn't that be 60 pi over 180?
1/3.
Now take into your calculator 60 over 180, and we get 1 over 3. So guys, this 60 degrees is equal to pi over 3. Is everybody comfortable with that? Now we have a tangible physical length around the circle. Okay, so 120 degrees. If this central angle is 120 degrees, the arc's 120 degrees. So now I'm asking you, what's the physical length of that? Well, we're going to multiply by pi over 180. So you'll take your calculator, because you know that's 120 pi over 180. Take your calculator, guys.
2/3.
2/3. Very good.
Oh, good.
This is 2, this is 3. So 120 degrees in radians is 2 pi thirds. So once again, if you wanted the decimal answer, you could type in your calculator pi divided by 3.
2 pi. Oh, yeah.
Right? Pi divided by 3. That's 1.04.
Wait.
And 2 pi thirds in your calculator, type in 2 pi divided by 3. That's 2.09. So once again, though, this is the exact answer. That's why we leave it in pi form.
2.09, would that be over?
Over 2.
4?
No, a full circle is 2 pi.
Right.
So that would be like, a full circle is, type in 2 pi into your calculator, is 6.2. So a full circle would be 6.2.
Oh,
So if you took...
2 pi is saying it's basically like 360 divided by 3.
Right.
It's equal to, right?
Yes.
In a way.
Yeah.
You can find the circumference of a circle by doing
Exactly! That is the circumference of a circle. Yes, exactly. We're going to make that connection later. Way to make it. Yes.
Okay.
So I'm saying 2 pi is like finding the diameter of a circle.
No, 2 pi wouldn't be finding the diameter. Well, 2 pi, you mean... No.
Saying 2 pi is like the diameter, or just like...
No. Okay, so guys, now we're going to apply that. So guys, if you notice, looking at these pictures, we didn't have a radius written down, right?
Right.
Okay, but, so we would assume our radius is 1 here. But now let's say that we have, can we have a circle with 60 degrees and then an even bigger circle with 60 degrees still drawn? So, but we couldn't call those lengths equal, right? Wouldn't one be bigger?
Yeah.
So we have to account the radius. So to find the physical length of any arc, you do have to account in what your radius is. So here's the formula for that. You'll take S is equal to R times theta. So S just means arc length. So S is arc length. So our arc length will be equal to radius times theta. Now theta does have to be in radians. We just talked about why. Because theta in radians is the physical length. But now we're going to take and we're going to multiply in our radius. Because we can have a 60 degree of a small circle and a 60 degrees of a big circle. And obviously those arc lengths aren't the same. That's why we have to account in the radius. So you're going to take your radius times theta. As long as your theta is in radians. Because we want physical length of an arc.
Is it possible for a theta that's not in radians even?
No, all degrees can be put into a radian. Yeah, good question. Okay. Do you have that written down and what it is? So here's my first example, guys. Stay with me, okay? We're kind of moving at a slow pace. So it says, find the length of the highlighted arc. So we want to know this length. So if this is 90 degrees, what's this? 90 degrees. But we can't say that the length of the arc is 90 degrees, okay? So we do know, though, that that's in degrees. Can't we change 90 degrees to radians? Okay, so let's do that. 90 degrees times by pi over 180, right? So that would be 90 pi over 180, which is?
Pi over 2.
Pi over 2. So 90 degrees is equal to pi over 2. So now we're looking at what's that physical length of that arc. Well, we have a radius of 3. So we know that arc length is equal to our radius times theta. So S is equal to our radius, which is 3 inches, times theta, which is pi halves, right, everybody? So times by pi halves. So then we multiply straight across, we get 3 pi half inches. So you guys, the physical length of that arc would be 3 pi half inches. Does everybody see how I changed theta to radians so we'd have a physical length? Then you just plug it into the formula.
So 3 pi is more than a full circle.
Right. 3 pi is more than a full circle. You're correct. Okay, let's do this one. Find the length of the highlighted arc. So first of all, we have a diameter here. So our diameter, since it's in the middle of the circle, it's the diameter. What's our radius? 5, right? Our radius is 5. Now, what's our theta? What's the central angle?
180.
180 degrees. Okay, so this is 180 degrees. Isn't this arc 180 degrees? Now, we need that in radians. So you take 180 degrees and multiply by pi over 180, which is
Pi.
pi, right? Which makes sense. Halfway around a circle is pi. If a full way around a circle is 2 pi, isn't halfway around a circle pi? So we're good. So 180 degrees is pi. So we know the physical length of this arc is radius times theta, as long as theta is in radians. So radius, which is 5, times theta, which is pi. That is just 5 pi, and these were centimeters. So the physical length of that highlighted arc is 5 pi centimeters. Questions? Okay. Let's do this one. Find the length of the highlighted arc. So we have 30 degrees here, and what would this be?
Okay.
What would this angle be? 180 degrees. Okay, so let's figure out what's the total here. 210 degrees. So isn't this arc 210 degrees? So we know that length of arc is our radius, which is, I'm putting it in 3. Radius is 3 times theta, which is 210. But don't we need to change that to radians?
7.
Can I just do it right here? Can I just, isn't it this going to be the same if I go times by pi over 180? Because with multiplication, does order matter? No, so I'm just going to do it all in one. So, let's type it into our calculator. 3 times 210 divided by 180.
376.
33 pi over 18.
33 pi over 18.
Here, Bob, so
So I typed into my calculator. 3 times 210, hit enter, divided by 180, and you get 3.5, 7 halves. Oh dear. Who typed that in?
me.
Masa. I got 7 halves.
Yeah.
Oh, yours.
Oh, sorry.
7 pi halves. Does everybody get 7 halves?
I got it. I got it.
Did that bother anyone how I converted and put it in the formula all at once?
I just did the old
Okay, well it's same thing, right? Okay, same thing. Hello. This one. Number 14. Here we go. Off the worksheet. We're gonna do this one together, then I'll let you work. So we're finding the length of the darkened arc, guys. So you can't just use, oh, I had people just saying I'm using 60, but that's not the darkened arc, right? So don't we need to find the angle that's in the darkened arc area? So let's think about it. If this is 60 degrees, won't this central angle be 60 degrees? Now isn't this a vertical angle to this?
Yeah.
So this is 60 degrees, so this arc must be 60 degrees. So then we know the length of the arc is S is equal to radius times theta. So the length of that arc will be our radius, which is 15, times theta, which is 60 degrees. Now, doesn't 60 degrees need to be changed to radians? So shouldn't we multiply that by pi over 180? Yeah? So now take your calculator. 15 times 60 divided by 180, 5. You get 5, so 5 pi. The physical length, and that was feet. So guys, if you were going to build, if you want to know how much physical feet that is, you would take 5 pi, hit enter, that's 15.7 feet. Does that make sense? I typed that in to my calculator, and then you know exactly how many feet. Does that make sense? So does everybody understand why we'd want it in not degrees? Okay, sweet. Okay, go. Okay, last thing to finish this off. This is pretty easy, but you should listen. So Braylon made the connection. So we know to find the length of an arc, the outside of a circle, or a length of an arc, you take the radius times theta. But theta would have to be in radians, right? So let's think about it. Isn't circumference finding the outside? Well, first of all, circumference is finding the outside of the circle, right, everybody? So circumference of a circle is the formula 2 pi r, which is actually r times theta, because 2 pi is the theta, right? Isn't theta 360 in this one, in a full circle? So isn't 360 in radians 2 pi?
I thought it was pi r squared.
Nope, it's just 2 pi r. So does everybody see how it's equal? Yeah? Okay, awesome. So circumference of a circle, you're just finding the physical distance on the outside of the circle. So you can use the formula 2 pi r, but you really are just doing radius times theta, because theta is 2 pi around the full circle. So let's find the circumference. Now understand, circumference means, once again, the physical distance on the outside of the circle. So with this one, since my diameter is 12, my radius is 6. So the circumference would be finding this physical length. So we'll do 2 pi times radius, since we're doing full circle. So 2 pi is theta, and then our radius is 6. So 2 pi r. So 2 pi times 6, our circumference is 12 pi. And that is a physical length, but once again, we'll leave it as a pretty answer, an exact answer, a mathematical way of writing it. 12 pi. Because then we're not rounding, we're using the full number there. Does everybody see how to find circumference? Yeah? 2 pi times radius. That's it. Are we all good? Just remember what you're finding, because a lot of people will be like, I don't even know what circumference is, but I can find it. Well, if you don't know what it is, then it does you no good. Okay, so these are what's required of you. Problems 3 through 5. You should be able to finish those really pretty quick. So circumference of a circle means the physical distance around the full outside circle. So it's 2 pi times radius.